Hello guys, please make sure if you have any questions on based on my part of the presentations to ask me or let me know so we can discuss further and help you as much as I can. So starting up, like the regression analysis, as you probably know, is a very valuable tool for a manager. Where we use the regression analysis is to determine the relationship between, for example, level of education and income. So the simple linear regression models, we have only two variables, where in the multiple regression models we have more than one independent variable. The variable to be predicted is called the dependent variable or response variable, which also the value depends on the value of the independent variables or explanatory or predictor variable. And as you see on the graph, the dependent variable equals the independent variable plus another independent variable. So in order to understand and investigate the relationship between variables, I found very helpful to look on the graph of the data. The graph is usually called the scatter diagram or the scatter plot, which normally the independent variable is plotted on the horizontal axis and the dependent variable is plotted on the vertical axis. And we're gonna be looking an example from the book on the following slides. So in our example, we saw in the book that the AAA construction company renovates all homes, which over the time the company has found that its dollars volume of renovation work is dependent of the area, and in our case Albany area payroll. In that case, as we see on the table 401 from the book, the sales is the AAA sales is our dependent variable, and our local payroll is our dependent payroll. So we're going to be investigating over the slides their scatter diagram and so on. So this graph from the book indicates the higher values for the local payroll to seem to result in higher sales for the company, but make sure to understand that there's not a perfect relationship because not all the points lie in the straight line, but we can see that there is a relationship, and a line has been the line that you can see has been drawn through the data to help to show that relationship, that the relationship exists between the payroll and the sales. The points do not all lie on the line, so we can understand for that, like there are some error involved in if we would try to predict sales based on the payroll using this or any other line. So like as you can understand, like many lines would be drawn through these points, and but how, like the question usually would be how we would recognize the best one for the true relationship. But here is the good thing that like Excel helps us a lot. Like we just put the data and it gives us the regression analysis, which will be providing the answer to this question. And again, guys, if you have any questions, please let me know. Before we move on with our problem, I would want to talk to you about the simple linear regression and understand the equation. So in any regression model, there is an implicit assumption which can be tested that a relationship exists between the variables. There is also some random error that cannot be predicted, and as you see, the equation is y equals to beta 0 plus beta 1 multiplied by x plus e, or e in Greek, as I'm Greek, and I wanted to mention that because I find it cool. So in our case, y is the dependent variable, x is the independent variable or predictor or explanatory, beta 0 is the intercept value of y when x equals to 0, beta n is the slope of the regression line, and e or e is the random error. The true values for the intercept and slope are not known, so therefore they are estimated using sample data. The regression equation based on this sample data is given as y hat equals to beta 0 plus beta 1 multiplied by x, where the y hat is the predicted value of y, beta 0 is the estimate of beta 0 based on sample results, and beta 1 is the estimate of beta 1 based on sample results. And again, like I want to remind you a lot of times, because while I was trying to understand it, it's good to know the equations, but Excel, if you have the data, Excel will be doing everything for you, giving your results. So there is not much to worry about, but I would recommend you to study this material so you are more aware of what you are doing and what you are finding. So going back to our example, the triple A construction example, we're going to be trying to predict the sales. So the dependent variable y in our case would be sales, and the variable we use to help to predict sales is the Albany area payroll. So this would be the independent variable. Although any number of lines can be drawn, as I said earlier, through these points to show a relationship between x and y, the line that will be chosen in the one that in some way minimize the errors is defined by the error equals the actual value minus the predicted value, and our equation for that is E goes for equals to error, and then the y is our actual value minus the y hat which would be our predicted value. So since errors may be positive or negative, the average error could be 0 even though there are extremely large errors, both positive and negative. In order to eliminate the difficulty on negative errors cancelling positive errors, the errors can be squared. The best regression line will be defined as the one with the minimum sum of the squared errors. And for this reason, regression analysis is also called as least squares regression. Many statisticians over time have developed formulas that we can use to find the equation of a straight line that would minimize the sum of the squared errors. The simple linear regression equation is y hat equals to b0 plus b1 multiplied by x. And also I've listed some formulas that can be used to compute the slope and the intercept. So in this slide, guys, you can see the preliminary calculations that used for the regression calculations for the AAA construction. Also, you should know that there are other shortcut formulas that are helpful when doing the calculations on a calculator, but they will not be shown here as the computer or Excel will be doing most of the other calculations on these chapters, so you really don't need to worry about that as much, but as I said earlier, it's good to know this material. So in order to compute the slope and the intercept of the regression equations for the AAA construction company example, we have x hat equals to sum multiplied by x divided by 6, which equals to 24 divided by 6, which gives us 4. And then we have y, which equals to sum multiplied by y divided by 6, which equals 42 divided by 6, which equals to 7. And then we have b1, which I said it equals to sum multiplied by x minus x hat, and then multiplied by y minus y hat divided by sum and multiplied by x minus x hat square, which that would give us 12.5 divided by 10, which results to 1.25. And then our b0 would be y hat minus b1 multiplied by x hat, which equals to 7 minus 1.25 multiplied by 4, which equals to 2. And therefore we have y hat equals to 2 plus 1.25x multiplied by x. Sorry. So to finish off with our example, as we can see here, if the payroll next year is 600 million, which x equals to 6, then the predicted value would be y hat equals to 2 plus 1.25 multiplied by 6, which it would give us 9.5 or $950,000. So really one of the purposes of regression is to understand the relationship among variables. This model tell us that each time the payroll increases by 100 million, which is represented by X, we would expect the sales to increase by 125,000 since our B1 was 1.25. This model helps, as we saw, it helped the AAA construction company to see how the local economy and company sales are related. So moving on into understand the measuring of the fit of the regression model. A regression equation can be developed for any variables x and y, even random numbers. We certainly would not have any confidence in the ability of the random number to predict the value of another random number, right? So how do we know that the model is actually helpful in predicting y based on x? As you saw in the AAA construction example, sales figures, which was our y, varied from a low of 4.5 to a high of 9.5, while the mean was 7. If each sales value is compared with the mean, we see how far they deviate from the mean, and we could compute a measure of the total variability in sales. So because y is sometimes higher and sometimes lower than the mean, there may be both positive and negative deviations, which simply summing these values would be very misleading because the negatives would cancel out the positives, making it appear that the numbers are closer to the mean than they actually are. In order to prevent this problem, we used three measures of variability, which is the SST, which is the total variability about the mean, the SSE, which is the variability about the regression line, and SSR, which is the total variability that is explained by the model. So in this slide, guys, we can see the equations for the measurement of our variability, which is the SST, which goes for the sum of squares total, which is sum open parenthesis y minus y hat squared, and then we have the sum of squares error, which is the sum multiplied by e square, which equals to our SST sum open parenthesis y minus y hat square. And here you need to understand that y is sometimes higher and sometimes lower than the mean, and like we would not be able to use x to predict y, so we would simply use the mean of y as the prediction, and then the SST would measure the accuracy of our predictions. However, in the regression line, we maybe use to predict the value of y, and while there are still errors involved, the sum of these squared errors will be less than the total sum of squares just computed. So moving on, the sum of square regression equation is SSR equals to sum open parenthesis y hat minus y squared. And also I've listed on this slide an important relationship, which is the SST equals SSR plus SSE. On this slide, you can see the sum of the squares for our company, the AAA construction company, which is the regression line is shown, and as is a line representing the mean of the y values, the errors used in computing the sum of squares are shown in the graph, which is the SSE equals to 6.875. Our SSR here is the 15.625, and our SST is the 22.5. So moving on, which I believe this part of our chapter is one of the most important things that we need to know, is the coefficient of determination, which to understanding the SSR, sometimes called the explained variability in y, while the SSE is unexplained variability in y. So the R2 that you see here is the proportion of variability in y that is explained by the regression equation that you see on the slide. R square equals SSR divided by SST equals to 1 minus SSE divided by SST, which for our example, the AAA construction company, we have R square, which our SSR was 15.625 divided by our SST, which was 22.5, equals to 0.6944. Again, remember that all those calculations, Excel is doing it for you guys, so just be aware of that. So this means that about 69% of the variability in sales Y is explained by the regression equations based on payroll, which was the X. If every point in the sample were on the regression line, meaning all errors are 0, then 100% of the variability in Y could be explained by the regression equation. So R square would equal to 1, and SSE would equal to 0. So the lowest possible value of R square is 0, indicating that X explains 0% and the variability in Y. R square can range from a low of 0 to a high of 1, and in developing regression equations, a good model will have an R square value as close as to 1. Another measure related to the coefficient of determination is the coefficient of correlation, which measure also expresses the degree or strength of the linear relationship. It's usually expressed as R, and it can be any number between and including 1 and minus 1. So the value of R is the square root of R square. It is negative if the slope is negative, and it is positive if the slope is positive. So in our case, for the AAA construction, the example with R square was 0.6944. So our correlation coefficient would be 0.8333. And we know it is positive because the slope is 1.25. And in this slide, you can see examples that illustrate possible scatter diagrams for different values of R. So On the first one, we see a perfect positive correlation, which our R equals to 1. Our second example to the right is a positive correlation, which positive correlation X, which is 0. It's bigger than 0 and smaller than 1. On the third example, we see no correlation, which are equals to 0. And our fourth example is a perfect negative correlation, which r equals to -1. So I'm gonna pass it over to Chelsea now, guys. But please let me know if you have any questions or need any help to explain you how you can do a regression analysis on Excel. And yeah, I hope you enjoyed my part, and yeah, that's it.
Firstly, I'm going to list the assumptions used in regression and use the residual plots to identify the problems. So the assumptions used in regression is the assumptions of certain errors we can make in a regression model. This can determine how useful the model is by performing the statistical tests. We can determine these errors from the assumptions of the following. For number 1 instance, the errors are independent. Number 2, the errors are normally distributed. Number 3, the errors have a mean of 0. And number 4, the errors have a constant variance, so regardless of the value of x. Why it is important to validate regression assumptions. Regression results cannot be trusted if any of the regression assumptions are being violated. For example, in the diagram presented, global warming may be reducing average snowfall in your town, and you're asked to predict how much snow you think will fall this year. So we need to consider the following assumptions. This includes the regression model in linear parameters, the mean of residuals is 0, the homodicity of residuals are equal variance, no autocorrelation of residuals, the x variables and residuals are uncorrelated, the variability in x values is positive, the regression model is correctly specific, and no perfect multi-correlated. Is there any questions about this? When identifying problems using residual plots, for example, businesses often use linear regression. If you were to start up your own business to understand the relationship between advertising and revenue, what are the errors you need to consider? So from looking at the diagram presented, we can see patterns of errors indicating randomness. So we can see the errors are independent, for one, and two, that it's not easy to predict because it's all random and it's scattered everywhere. Another example of residual plots when identifying problems can be non-constant error variance. For example, if a medical researcher were to analyze the plot below, determine the relationship between the drug dosage and the blood pressure of patients. So we need to consider the drug dosage for each patient and observe how the blood pressure responds. So as we can see, the plot has like a fanning effect where the residuals are close to zero for small and the x values are more spread out for the large x values. So the plot has like a funneling effect. As you can see in the diagram, it's all like spread out. So it starts really small, as we can see at the error side, and then we can see as it expands, it scatters everywhere. So that's why it's a non-constant error variance. When considering patterns of errors indicating relationship is not linear, for example, a professional sports team will measure the effect that different training regimens have on player performance. So this can include the amount of sessions they have weekly, such as weightlifting, yoga, stretching, hard sessions, soft sessions, everything to consider. And also we can consider how many points players score. So that may fall into a multiple linear regression. And looking at the diagram, we can see that one linear increases while the other decreases, which makes it a negative correlation. So from looking at the diagram, what can we see? We can see that it starts off small and it increases above the error, and as it reaches its peak point, it decreases. So this is why it makes it a negative relationship and not linear. When interpreting the f-test and a linear regression model, we need to consider the f-value in a linear regression model. Is to test whether all independent variables put together have any power to explain the dependent variable. So in the f-test study used in the linear regression, which is used primarily in the ANOVA and the regression analysis. This has several parameters involved at once in the null hypothesis. It is often to be considered a refinement of the more general likelihood ratio test, and it is considered as a large sample of chi-squared test. The f-test can be used in the special case that the error term is a regression model that is normally distributed. So note to self, if the null hypothesis consists of only one parameter, then the f and t test satisfy as f equals t squared, exactly. So that a two-sided t-test with d degrees of freedom is equivalent to a f-test with 1 and d degrees of freedom. An F-test and a linear regression model. There are 4 steps we need to consider. Number 1 is to specify null and alternative hypothesis. So this is an example of the H0 B1 equals 0, and also the H1 and B1 equals 0, 2. Then we must select the level of significance. So this includes common values such as 0.01 and 0.05. Then we must calculate the value of the test statistic using the formula F equals MSR divided by MSE. Then we must make a decision using one of the following methods, such as rejecting the null hypothesis if the test statistic is greater than the F value from the table in the Appendix D. Otherwise, do not reject the null hypothesis. Reject if F calculated divided by FA, dF1, dF2, dF1 equals K, dF2 equals N, take away K, take away 1. Or reject the null hypothesis if the observed significance level or p-value is less than the level of significance. Otherwise, do not reject the null hypothesis. So this includes the p-value equals p F calculated test statistic. Reject if p-value is negative A. An example of the F-test and linear regression model can include lower and higher income. In the diagram on the left presented, we can see the lower income and the higher income, along with the Y's and the X's. This is then interpreted into, on the right diagram, as a scatter plot, which includes the household expenditures by men. So to calculate this, we must consider the lower income as a reduced model, where the formula is yi equals b0 plus ei, and the higher income being a full model, where the formula for this is yi equals b0 plus b1 x i1 plus ei. Therefore, the appropriate null and alternative hypotheses are specified either as H0 B1 equals 0, H1 B1 equals 0, 2. So that is, the general linear F statistic reduces to the ANOVA F statistic, where the formula for this, as said in the previous slide, is F equals When using computer software regression analysis, Excel is one of the best sources for regression analysis using computer software. So how to use this is by first opening up Excel, then click the Data tab, which is above at the very top beside Formulas, and this will access where then you will select Data Analysis, and if this does not appear, go to Add-in to activate. Whereas when you activate this, this will be on your Excel when the next time you try to do a regression analysis. Then when the data analysis window opens, scroll down to and highlight regression, which then you will click OK as illustrated in the program. Do we have any questions or was I going too fast? So after we've completed the first step, we then move on to the second step, where the regression window will open. So as we can see where it says specify the X and Y ranges, we will input the numbers of X and the Y numbers presented. So this includes the Y sales and the payroll of X by the AAA construction company. The next step, we will check the labels box if the first row in the X and the Y ranges includes the variable names. After this, we will select the output range, providing a cell address to start the output. So this will include the specified location for the output. To put this on the current worksheet by clicking the output range and giving a cell location for this to begin. After this, we will click OK to have Excel develop the regression model, which will be the output that appears in the input range specified. Anybody have any questions? After completing this step, it will then move us on by interpreting the X and the Y by showing us the regression statistics, the ANOVA, and the residual. So as we see in the diagram, the intercept to slope is 1.25, and other information that was previously calculated for the AAA construction example. The sums of squares are shown in the column headed by the SS, so another name for error is residual, which is at the bottom. In Excel, the sum of squares errors is shown as the sum of squares residual. So the value is in this output are the same values shown in. So this includes the sum of squares regression equals SSR regression equals 15.625, sum of squares error residual equals 6.8750, the sum of squares total equals SST equals 22.5, where the coefficient of termination 1R2 is shown to be 0.6944. The coefficient of correlation R is called multiple R in the Excel output, and this is 0.8333. So, as we can see, the R squared in the regression statistics is a high R squared, which means it's close to 1. So that means it's desirable because it's 0.69444, which is above 50, which is more closer to 1. A low, less than 0.05 significance F p-value for overall model indicates a significant relationship between X and Y. So this is 0.039. Continues. The SSR regression, SSE residual error, and SST total are shown in the SS column of the ANOVA table, which is 15.65. The regression coefficients are given here, which is X variable 1, 1.25. Are we confused